So a chi-squared goodness of fit test, we are going to use the same concept of chi-squared test, but the distribution is going to be the same, the way we interpret the p-value will be the same, but instead of a table, we just have, a one by something, instead of a row by column table, we just have a column table of sorts. The number of pets a student has is claimed to be equally likely among none, exactly one, exactly two, or exactly three. There are 4 cases, and my claim is that they're all equally likely. So what is the probability that each of them would happen if I say they're all equally likely? Same, and what percent would that be? 25%, 1 in 4, right? If I pick the student, they are going to fall in one of those cases. So the null distribution is that the probabilities are the same. We'll get to that in a bit. So the claim is that they are equally likely, and the number of pets 0, 1, 2, 3. Those counts are from the sample that we collected, and that happens to be 2, 12, 5, and 2. Now, one major issue here is the counts doesn't exceed 5, but we can still do a chi-squared test in this case. So let's just do a chi-squared, even though these two counts are really small, has to exceed 5 or greater than or equal to 5. I don't want to change this because I collected the data here. So let's just go with it and see what happens. Based on this data, just by looking at it, do you believe that the claim is true? No, nowhere close to equally likely. So it's in 19, approximately equally likely 5, 5, 5, 5. Yes, in total I have 19. So I would want a fourth of the total sample size that I have, which is 19. So the observed counts are 2, 12, 5, and 2. Under the null, if they're all the same, and if I have 19 people, a fourth of 19 is 4 point something, right? I'm going to round it to 5. So the expected count is 5, 5, 5, 5. Yes, that is what I expect to get if the number of pets, if they are equally likely. So 2, 4, 6, 8, 10, 12. In red, I'm going to draw the observed distribution. So 2, 12, 5, 2. That's what it looks like based on the data. What is our null? Our null is that they are equally likely. The alternative, not equally likely. So, well, I am going to draw the expected counts in blue. So in red, I have the observed, the expected are in blue. So do they match visually? Not even close, correct? The expected and the observed, they don't match up at all. So even though to the naked eye, it looks like the claim is going to be false, we can't simply say the claim is false. We have to, provide evidence and do it properly, which is why we have a goodness of fit test. So we have the O's, we have the E's, and I erase this part. So what I'm thinking is it is more likely that we are going to reject the null and conclude that the observed data doesn't fit the claim, which is why we call it goodness of fit. It is not going to fit. That's my thought process as of now. We'll see. So we have the O's, we have the E's. We simply have to find the chi-squared for 0, 1, 2, and 3. How do we find the chi-squareds? From last time. So chi-squared for a single case is simply O minus E squared divided by E. Same formula here. So let's go ahead and plug in OE and use it and find chi-squared and the sum of all the chi-squareds, which would be our test statistic. So what is the chi-squared for 0? Yes.
1.8.
1.8 for 1. 9 point something. 9.8. Okay.
0. And then 1.8.
When we add all of those together, we get 13.2. It's simply the sum of all the individual chi-squares. So we can have 1.8 plus 9.8 plus 0 plus 1.8. It's 13.2. Good. Now, a chi-square test is always a right tail test, so the rejection region has to be on the right hand side. What does the chi-square distribution look like?
A little something.
Is it symmetric?
No.
No. Is it right skewed?
Yes.
Now we want to find the rejection region, which is going to be over here. And we are going to use that critical value to determine the rejection region. The area is 0.05. How did we find that critical value last time? So last time it was row minus 1 multiplied by column minus 1. We don't have rows here, we just have one row. If you did 1 minus 1, you get 0. So here, the DF is simply the number of levels. In this case, 1, 2, 3, 4, 4 minus 1. So I have the degrees of freedom. I know the alpha value, so how do I find the critical value? We use the table. So use the table and tell me what you get. So we have the degrees of freedom, which is 3. And we have to go to 0.05 because the value of alpha is 0.05, and 0.05 is simply the area of the rejection region. So it is the third column and third row. So the value happens to be 7.87. Yes, so the critical value is 7.87. So 7.87 is right here. Where is the test statistic? The test statistic that we found is 13.4. So 13.4, somewhere over here. Should they reject the no? Yes or no? Yes, because the test statistic falls in the rejection region. So we reject the null. The claim is true. Sorry, claim is false. The claim is that they're equally likely. They're not equally likely. Clearly, things are different. So we rejected the null and not equally likely. And we want to find the p-value. How did we find the p-value last time? This is a right-tail test. The p-value is the area above the test statistic. So press second bars. If you scroll down, get chi-squared CDF. You start at the test statistic, which is 13.4. Here is the question, even before you start this, do you expect the p-value, which is the area above the test statistic, to be smaller than 0.05 or bigger than 0.05? It better be smaller because it is the area above 13.4. So 13.4, E99, which would mean positive infinity. And what should go last? Degrees of freedom, and in this case it is 3. Plus Bren, enter. I get 0.0038. So the p-value is definitely less than alpha. So we reject the null. And if we reject the null, we can conclude that the claim is false, not equally likely. Based on the evidence, what are the chances that I would be wrong in rejecting the null? 0.3%. The probability is 38 in 10,000 chance. That's a small probability. So I can settle in rejecting. But do keep in mind, even though I did the test, I would be hesitant to do this, or probably wouldn't do this in practice, because those two counts are too small. They have to be 5 or above. I did it for the sake of an example. Good. So if you recall, we did the chi-square test using the matrix part. We entered the observed and expected, the observed counts and chi-square test. We got the answer directly. So we could do the same thing here, but instead of picking the regular chi-square test, which one should you pick? the GOF, which stands for goodness of fit. Also, the chi-square test would use matrices because we have a table, like tables, matrices. But here, we don't have a table, right? We simply have a column of values. So to perform the goodness of fit test, you have to use our lists. So go back to start, number 1. Oh, got all kinds of stuff here. So I'm going to clear all the lists, press start, number 4. I'm deleting all the data in the list, so bear with me. Got rid of them. So in list 1, I'm going to enter the observed values 2, 12, 5, 2. In list 2, we're going to enter the expected values 5, 5, 5, 5. Yes. Second mode to exit.
So, hey, what's that guy? Hey, Patrick, how you doing? I'm doing good. How are you?
Well, that's great. It's an ad. Somehow I clicked something. I didn't, you know what clicked. So list 1, list 2, and the degrees of freedom 3. And calculate. So that's exactly the value we have. Yes. So it says 13.4 for the test statistic, 0.0038 for the p-value, degrees of freedom is 3. And then you see something called CNTRB. Any guesses as to what that would be?
Oh, that's the value that we got,
Over
for us to
here.
do the kind.
Right, those are the individual contributions to the chi-square, the total. So the individual chi-square values are up there. Does that make sense? If I recall correctly, those get stored in list 3. So let's go and see for this. Oh, obviously not. Oh well. Good. So start branch is going to go easy on us. It's not going to give an error, it will probably run, but in practice, we can't use this because the counts are too small. Press start, goodness of fit, chi-square test. When you click, it says observed, expected. I define the column name for observed as observed, so select that. Expected is the expected column. And the rest you can leave it as is. So hit compute. And their expected value is slightly off compared to ours. And if you see, it says expected values have been normalized because they do not appear to be counts, proportions, or percentages. The reason being, the total of our counts doesn't exactly match the sample size that we had, correct? I had 19 people, the total count was 19. But when I divided it equally, I put 5 each. So in my case, I'm using 20, correct? So that one is not happy about it. It gives me an error stating that, oh, it doesn't match, but I did it intentionally. Like, if you want to be very accurate, you know, we can change all the, it's not going to change the conclusion. Do 19 divided by 4, 19 divided by 4, 19 divided by 4, 19 divided by 4. Hopefully it works. Observed, expected would be, what happened? Well, let's say all cells in equal proportion. So we get the same answer, yes. Like previously, it was 0.0053 at 5.25, 5.25, 5.25. Same answer. In the SPSS case, it looks like they rounded up to 21. 21 divided by 4 is 5.25. Yes, I rounded to 20 and put it equally likely. So rounding does come into play.